We Hello and welcome back to our Design of Experiments Fireside Chat for the month of April. For those of you who are new to the Design of Experiments course on Coursera, this is an event that we have monthly with a guest speaker, and we explore topics that are of interest to people in the experimental design community. Sometimes we talk about applications. Sometimes we talk about things that are peripherally related or directly related to the course. We always leave some time at the end for Q&A. This is a really good time for you to ask questions about the subject matter. And they could either be about the Coursera course itself, or it could be some specific question that relates to a situation where you're trying to use experimental design. We'd be happy to try to talk with you about that. For those of you that are on Coursera, there are recordings of these fireside chats, and they're posted in the course. You find them in the resources tab of your course. And I always encourage people to go back and look at a lot of these fireside chats. I think I just found out that this is like number 36. So there are quite a few of these, and the topics and things are just some absolutely fascinating topics. So would encourage you to do that. Okay, so now a couple of comments about how we actually run the course. When we're doing the course, please keep your microphone off and your video off, so we won't have any background noise or other disturbances that detract from the presentation. So please take care of that. When it comes time to do the questions, the best way for you to do this is to type the questions into the chat function on your Zoom menu. And you can do that anytime. You don't have to wait until the Q&A starts. You can start putting in a question anytime that you want to during the session. And we'll try to get all those questions answered during the hour of the fireside chat. And if we can't get them done, then we're going to respond to those in Coursera for those of you that are enrolled in the course. Okay, so I would like to now introduce our guest for today, and I'm really pleased that Marcus was able to do this. Marcus Perry is our guest. Dr. Perry is a professor of statistics, and he is in the Department of Information Systems, Statistics, and Management Science at the University of Alabama's Culverhouse College of Business. He's a very active researcher. His interests span all aspects of quality engineering. He's very active in a number of professional societies, including the American Society for Quality, the American Statistical Association, NBUS, that's the European Network for Business and Industrial Statistics, and the International Statistical Engineering Association. He is a past editor-in-chief of the journal Quality Engineering, which is an official journal of the American Society for Quality. And I'm really pleased that he was able to take the time to spend with us this morning. At least it's morning here in Arizona. And Marcus, I'd like to welcome you to the Fireside Chat, and please, the floor is yours.
Thank you, Doug. I appreciate very much the invitation to come and speak. Let me go ahead and see if I can share my screen here. Can we see the slides?
I've got it.
All right. Well, today I just wanted to share some of my thoughts on the joint monitoring of location and scale for what I'm going to term modern univariate processes. I'm going to preface this discussion because this is really a talk on monitoring. I'm going to preface this discussion on a very interesting discussion that took place in quality engineering back in 2008, led by Soren Bisgaard, with a number of different discussants, including Professor Montgomery being one of them. where the question was really asked, must a process be in statistical control before conducting designed experiments, right? And if you have not read this, this entire discussion, I really advise you to do so. It is incredibly valuable, and the discussants are very well-known individuals in this field. So very, very good discussion that I would recommend reading. I think we can all agree that if those who did read this and those who do read this, that we can probably agree that although a process need not be in statistical control to conduct a designed experiment, but knowing whether or not a process is in statistical control can certainly help in the designing of the experiment, right? And one example here would be, say, the amount of replication needed. If a process is deemed out of control, then we might expect a little bit more error variance than we would if it were in control, right? And so in order to sort of account for that, maybe one way that we could improve or maintain power for certain effect sizes is to increase the amount of replication. Of course, this is more costly. So certainly we would like to know whether or not our process is in control. The problem is that knowledge about whether a process is in control or not is not always reliably obtained. And this is particularly true for what I'm calling modern processes, right? So when I think of modern processes, say relative to what we might term traditional processes, I think of a minimum of three things. I think of individual data, individuals' observations, that is data that is not subgrouped, non-normal, and autocorrelated. So those are three. Now, if you think about obtaining data from a sensor, there may be some aggregation going on at some point, but there's issues associated with that as well. But this is what I feel is probably a minimal of what we would see with characteristics that we would see with modern day processes. Now, to facilitate monitoring in practice, what we tend to do is first decorrelate the original observations by working with, a time series model or residuals of a time series model, particularly of the in-control process, right? And to jointly monitor, meaning that I want to jointly monitor for changes in location or scale, to jointly monitor using individuals' data, the current sort of industry standard is to apply individual moving range charts to the residual process. Well, unfortunately, the IMR chart is incredibly sensitive to misspecification. In other words, it's important that we have normal and independent observations when we're using the IMR scheme. And this can be really problematic. And I kind of want to demonstrate that. I'm going to throw a little bit of math up. I'm not going to put a lot up, but I just want to demonstrate mathematically sort of the issue that we have here. So let's consider a continuous stationary process. We'll call that process Y. The notation I'm using here is just to note that Y sub t is a process. Suppose that the expected value of Y sub t is mu sub Y, the variance of Y sub t is sigma squared sub Y, and let's denote the lag K autocorrelation of the process Y as rho sub K. Let Y tilde sub t, let this just denote a centered observation. And suppose we assume an AR1 structure in computing the residuals, which is quite common. We do this a lot in practice. So our residuals are going to look like that, like you see on the screen, R sub t, right? This is what a residual process will look like. And it's not too difficult to show that the expected value of R sub t is 0, and the variance of R sub t would be given by that equation that you're seeing in 1. And clearly, it should be clear that if phi is equal to rho 1, then we've minimized our variance in that case. Okay. The problem comes here. The marginal density function of the residuals is given by that equation that you see in 2, and this f of y sub t minus 1. This is the joint density of y sub t minus 1. Okay, and it can be shown. It's not too difficult to show that if this joint density is in fact the zero mean bivariate normal density, then that the MGF, or the moment generating function of the density function in equation 2 is given by this in equation 3. some of us may or may not recognize this to be the moment generating function of a normal random variable with a mean of 0 and a variance given by this in equation 1. Right? So by uniqueness of MGFs, we can say that the necessary and sufficient condition for the AR1 residuals to be marginally normal is that yt minus 1 is bivariate normal for all t. So that becomes a problem. Clearly, if we extend this model out to AR2 or ARP in general, we because of linear combinations of normals, we find out that this we still must maintain multivariate normality, okay, in the y values. So this is a problem, is that it's easier to assume marginal normality on a variable, but it becomes more difficult to assume multivariate normality on a process. So this is problematic. Furthermore, I'll note that we can write the lag k autocorrelation for the AR1 residual process as that given in 4. And I'll note that that's generally not 0. The only time that that's going to be 0 is when rho sub k is equal to phi sub k, or phi of k, right? And that case happens when I perfectly specify my time series model. Well, unfortunately, that's probably not going to happen in real life either. So, the residuals are only uncorrelated when the time series model is perfectly specified. So this sort of raises some concern with respect to applying individual moving range charts to residual processes, right? It seems somewhat naive to assume that these processes will be normal and independently distributed. And folks might say, well, what's the consequence here? Well, the consequence is that when the model assumptions are violated, it becomes very difficult to control the false alarm rate of these monitoring schemes. And it's been my experience with practitioners that when sufficient control of the false alarm rate is challenging, practitioners lose confidence in our methods and they don't use them. I have an old a colleague at Budweiser years ago that I had said, what control charts do you use, et cetera? And they said, oh, we don't even use them anymore. I said, well, why? He said, because every time we use them, the points just plot outside of the limits, and we can't really make a decision on that basis. So this is a real problem. Let me demonstrate to you using a real process the frustration of the modern day practitioner, or in fact, the modern day process monitoring practitioner. So I want to use the data that comes from Bianca Colosimo and Marco Grasso's 2018 JQT, Journal of Quality Technology paper. It's a data that's collected from a selective laser melting process. It's an additive manufacturing sort of process. And the authors were concerned with detecting hotspot occurrences in a laser powder bed fusion process. Now, data to facilitate the monitoring was not collected by hand, in subgroups. It was collected by video capture. And obviously, any video can be broken down to a time series of frames. What I'd like to do really quickly is just show you this process. So I'm going to stop sharing my slides for a moment. I'm going to share a video of the manufacturing process. It's a melting process. So I'm going to press play. So there's about 6 seconds of video here. I hope it's going. There we go. And we notice in the upper right corner, we get this hot spot that occurs. That's a fault. That's something that we want to detect as soon as possible, as soon as it starts to occur. So I'm going to run this again one more time so you can see we have the tool, the melting tool that's going across, and it's melting this part in the shape of a triangle. Okay, so let me stop sharing that and go back to my slides. And so these two pictures that you see on the slides here are, the leftmost picture is just indicating the 3 vertices at which a hotspot could occur. Okay, and it's also the red outline is just sort of going over the trace of the part where the melting tool is going, so the pathway. The picture on the right is showing the melting tool and the hotspot at Z that occurred. Okay. Now, if we wanted to look at time series plots for each of these vertices, we have these here. So we have the topmost is the time series plot at vertex X. And what we're measuring here is what we're calling the response here is intensity, okay? So the intensity at X over time, the middle plot shows the intensity of Y over time, and the bottom plot shows the intensity of Z over time. Now, I'll note that we've got that the locations X and Y are in control locations. These are locations where this is normal, sort of normal melting behavior. On the other hand, location Z does show a hotspot, which is characterized sort of by this really slow downward trending data, right? Which in some senses, early on, could be characterized by an increase in location, or also could be characterized by a decrease in scale, okay? So what I want to do here is I want to use, since I have 3 different locations, this is probably not ideal. Ideally, I would like to have a whole nother replicate, but I don't have a whole nother replicate. So what I'm going to do is I'm going to treat location X as a training location. I'm going to train everything on that. And then I'm going to treat vertex Y and Z as sort of test locations, okay? So the first thing that we would do in modern practice, the first thing, not in modern practice, the first thing we would do according to the industry standard is to fit a time series model. Let's use location X to do that. So what you see on your screen now is a subplot. The top plot here on the left is the original time series at location X. The bottom plot is the AR1 residuals, okay, that we fit. And I believe the AR1 model had an estimated fee of around 0.9 or 0.92, something like that. I didn't put the actual model parameters in, but nevertheless, we see that the residuals on the right here in plot B, as expected, are not going to be normal unless we can say that the joint distribution of the intensity at location X is jointly normal. Then we can't say that the residuals are normal, and this is clearly shown here. But another thing that tends to happen is that the model misspecification, clearly this is not exactly an AR1 model. This is something a little bit different. And you can tell that because if you look at the sample autocorrelation function of the AR1 residuals, we still have a little bit of autocorrelation caught in those residuals. Now, certainly we could try to fit a higher order model in AR2 or something to this, and could probably get it to where in phase 1, we've removed the correlation, but there's no guarantee that that's going to remove the correlation for phase 2 data because the model's probably wrong. So what I'm going to do is I'm going to plot the residuals, the AR1 residuals on an IMR chart, which is sort of the industry standard. And when I do that, I get this. And this is exactly what my colleague was talking about, that this is an in-control location, okay? The control chart here was designed so that the in-control average run length is 500, right? And so there's clearly a challenge here with respect to controlling the false alarm rate. One might suggest, well, just increase the limits. Well, we could, but I don't know what that in-control model is, so it's going to be difficult to know what the false alarm rate is, right? So this is problematic. So what I want to do now is I want to apply the IMR charts to the test data at Y, right? So the parameters for the chart were estimated using location X, and I'm going to plot the residuals at location Y, and I still get this problem, right? So again, riddled with false signals. I don't know if there's not too many. If you're basing your decision on whether or not you're getting points out of the limits, well, then this is probably not a very good solution, okay? And I think even more, not more troubling, but also troubling is the fact that if we look at location Z, we're not able to even detect the change, right? We're not able to detect that hotspot. And this is primarily because that hotspot can be characterized by a decrease in the scale of the process. And so we know that the moving range chart is not capable of detecting decreases in scale. So really problematic. So I view this as something that that can really frustrate practitioners who are trying to use the current methods. In other words, trying to adapt traditional views to modern data sometimes doesn't really work out very well. So the question, well, what is an alternative scheme? What's an alternative joint monitoring scheme? Well, there are non-parametric schemes, and that would seem to be the way to go. The problem is that there are not a lot of non-parametric schemes for joint monitoring of location and scale that use individual data, right? They have to use subgrouped, right? Additionally, because we're probably not going to specify that time series model exactly correct, we can probably expect there to be some smaller traces of correlation, of autocorrelation in the residual process. And it's pretty well known that many non-parametric schemes break down in the presence of autocorrelation because they were designed for the independent process. And so there is a paper that a student, a PhD student of mine, Ji Wang, wrote and published in Journal of Quality Technology in 2022. And I more recently have made, I guess, improvements to that approach in another paper that's currently out for review. If you're interested in that paper, please let me know. I'm certainly willing to share it with you. But what we did was propose a joint monitoring scheme for individuals' data that doesn't require any distributional assumptions and can actually incorporate autocorrelation quite easily. And of course, the ideas behind doing this are to basically take this complex sequence that we're dealing with, and let's extract a couple useful sequences. In fact, we'll extract from it a couple binary sequences, okay? Because binary sequences are a lot easier to model. One of those sequences I'll term the median clip sequence, meaning that if the continuous observation at time t is greater than the median, the in-control median, I'm going to assign the median clip sequence a value of 1, otherwise 0. So we get this binary sequence of information on the location of the continuous process. A second sequence that we could extract out would be the IQR clip sequence, meaning that if the observation at time t is outside of the in-control IQR, we're going to assign it a value of 1, otherwise it's a value of 0, okay? And so we get this IQR clip sequence that has useful information about the scale of the process, of the continuous process. A couple nice things is that when the process is in control, the mean and variance of either one of these sequences, or the mean and the standard deviation, are both equal to 0.5, 1/2, okay, for any process, for any continuous process. Secondly, if the process is in control, then these two sequences can be shown to be independent. Okay, and so the joint monitoring strategy involves the simultaneous charting of individual QSUMs on the binary sequences. But keep in mind, these binary sequences are likely going to have autocorrelation. So you have to incorporate that autocorrelation somehow in there. In the first paper by Ji Wang and I, we considered modeling the joint mass function of the binary sequence using a very simple approach called a Bahadur approximation. There are problems, it's very practitioner friendly, but there are some constraints on the types of QSUMs that you can come up with with that parameterization. So what we did in the recent paper was to replace that Bahadur approximation of the joint mass function for the binary sequence with a copula model. And it works really, really well. It reduces the number of parameters needed. It's a true likelihood function, so we can use maximum likelihood estimation in phase 1, et cetera. Okay, so this is sort of the strategy that I want to use. So let's go back to that selective laser melting process and see. And I just want to point out, I don't get into the technical details here. For those who are interested, I am certainly willing to send you the paper to dig through. And if you have questions on any of the technical details, please feel free to reach out to me. But I want to go back to the selective laser melting process. What you're seeing on the screen here is the time series at location X. So we have the original sequence, and we have the AR1 residual sequence that we see on the bottom plot. Now, we could certainly clip the original sequence if we wanted to, but let's go ahead and clip the residual sequence, since that residual sequence has less autocorrelation. So we'll clip that residual sequence, and when we do, notice that what you're looking at on the screen now are sample autocorrelation functions for the median and IQR clip sequences. generated from the AR1 residuals at vertex X, okay? And so notice that we've got a little bit of autocorrelation going on that must be considered when modeling those binary sequences. Otherwise, it's difficult, even for small traces of autocorrelation being present, it's difficult to control that false alarm rate of the monitoring schemes. So what I outline in my paper is sort of some model selection strategies for choosing the order. You could probably use a partial autocorrelation function plot here as well to kind of get an understanding of what order is needed. But we could also use the Bayesian information criteria, okay? And so we're looking for the order for this. The first row is for the median clip sequence. The second row of the table is for the IQR clip sequence. And if we look at the minimums, we see that the median is probably good to model the median clip sequence with a second order dependence, and probably good to model the IQR clip sequence with the first order dependence, right? So, and again, I just note here that the technical details are given in the paper, and I'm certainly willing to share. The technical details for these QSUMs and their derivation are also given in the paper. But I'll note that here's the proposed median and IQR clipped QSUMs, which were each designed for 50% increases in the mean proportions, right? Meaning that the proportion of observations, the proportion of continuous observations that are observed to be above the in-control median or outside of the in-control IQR, okay? And we see that these charts, similar to the IMR charts that I talked about earlier, are designed for an in-control average run length of 500, so they're sort of equivalent in that sense. And we notice we don't get any false signals, which is very good. We don't want those false signals, okay? Let's take a look at the performance when applied to the Y location, vertex Y. Again, we get indication that there's no strong indication that this process is unstable, right? There's no indication. However, if we take a look at location Z, we do see the change, okay? In fact, we are able to detect a slight increase in the proportion of observations that plot above the median, okay? But we don't see any increase in sort of the scale, all right? Now, a nice thing about the alternative scheme is that unlike the IMR scheme, decreases in scale can be detected, okay? And so let's take a look at that. It's very simple to apply this to decreases. You just have to modify the clipping scheme. Very simple, and apply the same QSUM design that was proposed in our papers. But we see that this is at vertex X, and again, we shouldn't see any out of control points because it's an in control location. We also have for the Y location, we don't see any decreases, but very nicely we do see in the IQR clip chart, we do see that increase is detected, that decrease in scale is in fact detected. So this is what I view to be a very practical, because it's not overly challenging. In the case of the sorry, someone was at my door. In the case of the Bahadur approximation, everything is closed form for the most part. You're using moment estimators. In the case of the copula model, there is a little bit of numerical activity that needs to take place. It's a little more computationally extensive, but most of that additional computation occurs in phase 1, not in phase 2. So it really doesn't have a huge effect on phase 2 monitoring. Now, are there criticisms? Of course, there are criticisms. There's always going to be criticisms, okay? But it usually depends on who you ask, right? So a data scientist is going to say, well, you're not using all available information. And that's true. Certainly that opens up some lines of research to say, well, what other sequences could we potentially extract from our complex process that would be useful tools for us to solve our problem? On the other hand, the process engineer, which I am by degree, says, well, I want a solution to this. I want a solution that's interpretable, right? So that I can understand my process better, okay? But for those who do, who are critical about the clipping strategy, I still think that, it's certainly possible to plot all your continuous charts, but let's control that false alarm rate. And that clipping strategy could be run alongside one of those continuous charts in order to attempt to better control that false alarm rate when used with modern processes. So as the last note that last thing that I'll point out is that we have extended our ideas for the univariate data to multivariate case. And so the problem with that is when you start getting greater than, say, trivariate cases, you get 4, 5, 6 variables, it becomes somewhat challenging in terms of the number of parameters that need to be estimated, because you have to consider the cross correlation at time t, you have to consider the autocorrelation and the dependence order of that autocorrelation, and then you have to consider whether or not the variable 1 at time t is autocorrelated with variable 2 at time t minus 1, and there's parameters there and so forth. So as you start to increase the dimensionality, it can become somewhat, not very parsimonious in that sense. But I just want to, if I still have some time, I just want to go. Let me go through a study that I did, because I didn't present any studies in this presentation, but I want to talk a little bit about whether or not the alternative strategy is robust to model misspecification. Okay, and in fact show how unrobust or sensitive the IMR scheme is to misspecification. So let me talk a little bit about this study. It's about 4 slides. So suppose the true process is assumed, now that's the key word, assumed to follow an IID normal error AR1 model with parameter phi. Okay. Now, if this specification is the correct specification, then the autocorrelation function here will be given by rho sub k equal to phi to the k, right? That would be the autocorrelation function if in fact it's true. And consequently, the residuals here would be normal and independently distributed. Okay, so for comparison purposes, I'm going to refer to this model as the Gaussian model. Okay, let me introduce some slight deviations from the Gaussian model. Okay, I'm sorry, this reference here has a question. My apologies. When I send the slides to you, Doug, I'll make sure that that's fixed. Okay, so what we're going to do to sort of deviate slightly from the Gaussian model is to use a couple different copula models. Okay, both of them are going to be symmetric, but they're a little bit different, right? So we're going to use the Frank and the Plackett bivariate copula models in our study here. And so you see on the screen here, you see 3 different models. The A is the Gaussian model, B is the Frank, and then C is the Plackett. Let's take a look at these from a conditional. So these are the joint distributions, or the joint contours. Let's take a look at the conditional distributions of y sub t given y sub t minus 1. Okay, and what we see here is for the Gaussian, we see that the only moment that's a function of y sub t minus 1 is in fact the mean. Whereas in the Frank and Plackett models, we have higher order moments, not just the mean, but variance, skewness, etc. That are also functions of y sub t minus 1. So these latter 2, the Frank and Plackett, are sort of examples of what really happens in practice. We're going to have that dependence many times, not just with respect to the mean, but with respect to other moments of the distribution. If we want to look at the autocorrelation function of the and sort of compare the autocorrelation functions of each of those processes, that being Gaussian, Frank, and Plackett, in the left here, we see that the autocorrelations don't seem to deviate too much. We see that, well, that might not be too much of a problem. And on the right-hand side, we see that, well, the autocorrelations are only 0 for the Gaussian case. Okay. Further, we could look at the probability density functions of the AR1 residuals, and we see that they don't deviate too much. So we might feel that there's probably not going to be much of a difference with respect to the performance of the IMR chart. Well, that's not true. So what we did here was we ran a bunch of simulations, and we compared the in-control average run length. So this is with respect to the in-control average run length. So this is what I'm concerned most about, is the ability to control that false alarm rate. And we see that for different values of rho 1, which is the first order autocorrelation for each of these processes, we find that if the true process is Frank and we use an IMR chart to monitor it, the in-control average run length is going to be about 44% smaller than what we had expected to be if our assumption was correct, the assumption of a Gaussian process. And certainly that increases as the magnitude of the correlation increases, right? It increases to 80%. So there's with respect to the Frank process, the in-control average run length is 80% less than what we had expected to be. So this is problematic. If we compare it to the alternative, we see that not only do we get better, right, results in other words, for the alternative case, the Frank, if the process is truly Frank, then the true in-control average run length is about 6% higher than what we'd expect, right? So the in-control ARL that was obtained under the assumption that the process is Gaussian is sort of a lower bound on what that in-control ARL is under the alternative case. So we feel that the IMR chart is very sensitive to even slight deviations from the Gaussian model. And the alternative approach, even though I could design it better than what you're seeing here, I'm just basing this on the fact that let's assume that the true process is Gaussian when it's actually Frank. And we see that we don't get too much problem. Certainly when the correlation, the first order correlation gets higher and higher, we get more and more conservative, essentially is what we're seeing there. So I think this study, along with several others, are included in the recent paper that's currently under review. And as I said before, I'm certainly willing to share both of these papers with the audience. So with that, I am happy to take any questions that you might have.
Thanks, Marcus. I got a couple of comments. One of the points that you made on one of your slides was that there's been some criticism of the methods, and it seems to be coming more from the statistics and data science folks than from the process engineering people. And that reminds me of a joke that Stu Hunter told me years ago. And I've always admired Stu's sense of humor, and this is a great one. He starts off. He says, "Doug," he says, "what do you call a collection of dogs?" Well, I said, "Okay, it's a pack of dogs, right?" And he says, "And what do you call a collection of cows?" Well, that's a herd. And he says, "Well, what do you call a collection of ducks?" Well, that's a flock. And he said, "So what do you call a collection of statisticians?" And I thought for a while, and I said, "I give up." He said, "A collection of statisticians is an argument." It's an argument of statisticians. I just loved it. I thought that was great.
Yes. I mean, that's true. It's true. Look, my view of this is that processes are becoming so complex that it becomes, certainly people say, well, let's apply machine learning. Okay, but how interpretable is that now?
Yeah.
There's not a lot of interpretation going on. There's a fitting of a model with 100 parameters that those parameters are not interpretable. So when I develop methodologies, I try to make sure, as an engineer myself, I try to make sure that the practitioner, that this is a tool developed for the practitioner. And I think many times, unless you have incredibly sophisticated modeling capabilities, you may not get the opportunity to control that false alarm rate very well. And that's a problem moving forward in our research.
What about implementation in software? Where do you stand on that? Because this, in order to be able to use this, you're going to have a software implementation that's accessible.
Yeah, I mean, are you asking, do I have?
Yeah.
Do I? Yeah. So, yeah, absolutely. Yeah. This would not be right now. I have it in MATLAB, programmed in MATLAB, and that can actually be converted very easily with the MATLAB coder into C or C++ languages, which then could be brought into an R package, right? So I do have a student who is interested in putting this into an R package, but anybody who, the main issue with respect to the copula-based parameterization that I talked about in the second paper is estimating those parameters. And it turns out that it's not overly difficult. You just need to, you'll have to use numerical optimization routines because there's no closed form for those copula parameters, which are in fact related to the correlations. But to answer your question, that is something that is in the works so that I can get it out to more practitioners to use.
Because that would be extremely useful.
Yeah, I think so too. I appreciate that.
The other thing that occurred to me when I was looking at your at the video graphic is that I've run into a lot of applications of design experiments where the response variable is actually a time series. You know, when you do a particular treatment combination in the experiment, you don't get a single number. You know, you get a time series, and it seems that some of what you're doing here would be applicable to the case where you have a time series output. And you know, I've always kind of struggled with ways to deal with that in a good way. You know, typically what you end up doing in a lot of those experiments is you capture some of the salient features of the time series and use that as a response. You know, you use maybe the average or the variance, or if you know, if there are other features of the time series, you try to compress it to a single number.
Right.
And I've never been overly happy in doing that. And so I'm thinking maybe some of what you're talking about here, some of the ideas you talk about here could be adapted to dealing with time series responses.
Well, that would be great to investigate that. I would, if you have any references you can send to me, I would love to
Yeah,
take.
I'll look around. I know I've looked in the experimental design literature from time to time, looking for you know, either papers that talk about a time series response or a
Functional response.
yeah, and I've had limited success in finding anything, and you know, I've done a couple of things myself in practical situations working with a consulting client, but you know, never felt like I did anything all that wonderful. I should think about writing it up and offering it as general advice. But I just wondered what your thoughts were on that. Because there are a lot of situations where the response variable is a time series.
Right. Yeah, I haven't thought a lot about it. I mean, it's something that I would be interested. I think what I would love to see somehow is sort of a merging between sort of the time of signal in process monitoring and how we can sort of use a systematic strategy for causal. Because right now, you know, if we get a signal, we're sort of guessing at what the cause is, and correlation does not imply causation, sort of things. And so experiments are really used to sort of decouple that. And I think there could be, you know, potentially with using maybe, you know, I think Stefan Steiner has a really good statistical engineering algorithm that could be. So I think a lot of this needs to be revisited for modern processes. You know, the stuff that we've learned many years ago and beginning, you know, intro to process monitoring. I think, you know, if there could be some way to sort of bring experimental design into the you know, into an entire sort of how I'm trying to describe it there, but something that can help us to sort of identify the true causes of these changes, the true root causes. And I think that's missing. I think, you know, to the most that has been done is more sort of correlation analysis, and here's where the change point occurred, and so you need to be looking around these locations and take a guess at what big event might have occurred. It'd be nice if there was something a little bit more systematic for the practitioner to do when the signal occurs, because nobody really talks about that a lot.
You're right, and this whole business of the false alarms, which you addressed, is extremely important. In fact, if you go back and look at the foundations of process monitoring, and what Schuhart talked about, that's why Schuhart settled on using 3 sigma limits on control charts, is that he found from practical experience at Western Electric that if you use narrower control limits, they got false alarms, and the engineering and operating personnel would in a very short period of time start ignoring the signals,
Right.
because they would go out and look diligently for some sort of assignable cause in the system, and a lot of times they wouldn't find anything,
Or they would modify the process wrongly.
yes.
And all the money that was and resources that were spent to optimize a process is now sort of messed up. So
Well, and that kind of tinkering just usually causes more signals.
Right. Right.
So I mean, it really is kind of an important issue, and I've wondered myself, is there a nice way to tie designed experiments into this business of hunting for assignable causes?
Yeah.
And I think there probably is, but it requires a lot of thinking about how to actually design the experiments that you're going to run. And then you also have the problem that if the process isn't stable, the sample sizing questions and issues of blocking and things like that become a lot more complicated.
Right.
And dealing with that is not easy. But I really appreciate your referencing that paper by Soren Biscard,
Yeah.
because there's a lot of really good information.
Absolutely. Yeah.
There's a lot of really good thinking in that paper, and I really encourage anybody that's really doing experimental design work to track that paper down and take a look at it. I think it's a 2008.
2008 issue, volume 20, issue 2.
Yeah, it's I was one of the contributors to that. I don't know that I had anything very useful to say, but
You wrote a really nice, really nice and understandable. If you've of course, most of us have read most of your books and are very adapted to your writing, and I think it was very clear. It was very nicely written.
Well, there's a lot of good advice in there from a number of people, and I really encourage anybody that's trying to use designed experiments, particularly in complex processes, to think about process stability and control as you're planning to run the experiment, because it may be that there are even certain time periods where a process is known to be either more or less stable.
Right.
Maybe right after startup, it's
Right.
it's less stable than it is, a week or two into operation, and you also have to think about, do exogenous events affect the process that could affect the experiment. I remember a project I had a few years ago, was a consulting job with some people that were, this was really an interesting process. These folks are growing human skin.
Wow.
Wow. And you say, well, what do you need to do that for? Well, treatment of burn patients,
Right.
and treatment of people with diabetics, with diabetes. Because if you have to do a skin transplant, for a diabetic patient, you often can't use their own skin. You can't take it from another part of their body and plant it on their foot or wherever they need to address the lesion that's growing there, because their body's already infected with diabetes, and so it doesn't, the treatment doesn't work. So growing this artificial human skin, there's a lot of applications for this, and they had a reactor in which they could grow this stuff. And they used they had starting material that came from the residuals that's left over after birth. Okay, so they used some of the leftover biological material from human birth. And anyway, we were running experiments in this reactor trying to optimize this, and we kept running into certain test combinations that produced absolutely ridiculous results, absolutely crazy results. They were so unreasonable that the biochemists would look at it and say, this is just wrong. Something's wrong. And we couldn't figure out what it was, what's causing this. And I sat down with one of the operating guys, and we started looking at when did these erroneous observations occur. And they always occurred, it turns out, overnight. They occurred in the overnight hours. And this is a 24/7 process. This reactor runs 24/7. And it would have to run for typically a couple of days for us to be able to get a response reading for a particular test combination. But it turns out that what was going on is, once we figured out when it was occurring, is it had to do with the HVAC system in the laboratory. On certain days, the HVAC system would cycle off at night, and the temperature in the lab would go up from 72 or 73 to like 80 or 85 degrees, and then the system would come back on again, and it would cool off. Yeah, and it turns out that the reactor itself was very sensitive to ambient temperature. So
but that was causing some issues with regards to the responses you were getting.
Absolutely. And it was essentially an out of control situation in the process that dramatically affected the results. Right. And this is why I think understanding process stability is so important in experimental design work. And if the process isn't stable, what sort of steps do you take to deal with that? Right. It's really important. Right. And I think you've made. I hope people realize what you're doing is you're making us aware of this problem. Right. And how much of a problem it can be in
it was a problem before, but with today's sort of process, when we the old Schuhart days of how we collect data are gone. I mean, we collect data differently now. We can't expect our observations to be as they were many years ago, when we're walking out to the assembly line with a quality control table and a caliper.
Right.
It doesn't really it's not like that anymore. And a lot of the traditional methods were designed for that. Central limit theorem was going to justify normality, and the fact that we're taking observations every hour, which is going to sort of help with the autocorrelation and so forth. So I think it's an important problem. And I'll never forget that the colleague of mine who had said, oh, we just don't use those anymore because we don't believe in them.
Wow. By the way, we have a question that just popped in. I don't think you can see it, so I'm gonna read
Yeah,
it.
I do see here. What a gauge on our study, would a gauge on our R&R study help with identifying sources of variability? Absolutely in a phase one.
Yes.
Okay, if there's a phase one where you're trying to maybe bring an unruly process into control and trying to identify sources of variation so that you can then attack those particular areas, absolutely.
Yeah.
In phase two, perhaps after a signal occurs, but you have to know whether or not that signal is genuine or not, and that's
Yeah.
the question.
Yeah. If it in fact is not, if it is a false alarm, then you've got issues, and uh, that's why I think understanding what sort of signals you're getting, and hopefully you do have some sort of process monitoring scheme, and you understand it's type 1 error rate. That's why it's so important. But yeah, definitely in phase one, gauge R&R studies are really important, and they can help you with a lot of things, because a lot of times it's the measuring system itself that is part of the problem. Uh, an unreliable measurement system can complicate your life a lot, and particularly in a design experiment.
Garbage in, garbage out. That's
You're
what you do.
critically dependent upon the reliability of the measurements, and things can go wrong in a hurry if you don't have that. So that's a very good question, and I appreciate that being brought up for us to think about. Do we have any other questions that we want to try to?
One just popped up. So it says, interesting example, one requirement in a regulated environment is that the equipment qualification process accounts for elements that could impact equipment performance as it relates to its intended use. This includes temp, humidity. So just a comment by
Yeah,
Augustine.
yeah, and that is a very astute comment that we need to be aware of. And that's, I think, even though that's clearly a requirement for regulated industries, like pharmaceutical products, for instance, it's it's something to be alert to and aware of in any kind of experimental situation. I think it's really, really important. Many processes are affected by environmental factors or exogenous events that affect performance, and running experiments in processes that are subject to those kind of problems is often difficult. I can remember some years ago working with people that were developing a process for a new pharmaceutical product that was going to be delivered to the patient as a tablet. Okay, and we did a lot of experimental work on the formulation of that tablet, so that it could be easily manufactured on a tablet press without crumbling and falling apart and that sort of thing. And we had great success with this. And then they started actually manufacturing the tablets, and disaster struck. The tablets would crumble and fall apart, and it was awful. And it turns out that the lab where the development work was done was perfectly temperature and humidity controlled. The manufacturing facility where the actual tablets were made did not have any environmental controls at all, and humidity raging around all over the place, and that's what was causing the tablets to crumble as they came out of the tablet press. So you know, lots of interesting things happen. We are getting to the end. It's basically 10:30 my time, and we like to finish on time. And Marcus, thank you so much. I've found this to be a fascinating talk, and there's just a lot of pieces to this that we could talk about even more. And I do encourage people to track down the Soren Biscard paper, because it's got a lot of good information. Our next Fireside Chat is going to be in August, and more information about that and about who our guest is going to be and the timing is going to be in Coursera. And as I've mentioned before, you can find the past recordings in the resources tab in Coursera. And I appreciate everybody that came today, and we look forward to seeing you in August. Again, Marcus, thank you very much. I appreciate your taking time out of your busy day to help us out with this.
I appreciate the invite, Doug. It's always a pleasure.